Hi everybody. Yeah, I'm waving because we're finally done with the electron for a while and we're moving into waves. So, might be Jonah's favorite topic. All right, we live in Florida, we see waves. Let's try to understand what's going on with them. So, first of all, there's lots of kinds of waves. There's not just waves that you surf on. There's electromagnetic waves, there's earthquake waves, there's sound waves, light waves, microwaves. There's a lot of waves. There's the queen wave, where she does this. All right, but the main thing to remember is waves are a way or a vehicle or a process in which energy gets transferred. All right, so let's break this into two types and then two ways of travel. Okay, mechanical waves require a medium. All right, sound has to travel through something. Earthquakes and water, go through materials. Electromagnetic waves do not require. They can travel through a vacuum, which is part of how the sunlight gets to us. So all of the electromagnetic waves, we'll spend a little more time on those another day, but they all travel the speed of light. So even though we call it the speed of light, it really is the speed of all the electromagnetic waves. Now, how do they move around? Well, there's two propagation methods. The first one is called transverse. Transverse causes the medium, and I'm going to either have you watch a video or we're going to show a demonstration, so there'll be a little visual for this in a minute or so. When water waves travel, think about a water wave. Think about a boat sitting on the water. As the waves go by, the boat goes up and down, up and down. The wave goes this way, the particle, meaning this time the boat, goes up and down, perpendicular. Longitudinal waves are a little bit different. They're called also compressional, and sound is the best example of that. And it literally will squeeze air particles super, super tight, so I'm going to make them super tight, and then it releases them, and then it squeezes them super, super tight. Zoom. Okay. And then they loosen, and then they're super, super tight. So there's still kind of an up and down feature. This part here is actually called the compression. The part where it releases is called a rarefaction. And again, I'm going to show you a little video on that as well. Well, I'm going to show you a demonstration or a video. But that's how sound waves work. When you hear, sometimes sounds can hurt because they push. You can actually feel them pushing on your eardrum. All right, so let's go through the main parts of the waves. And I know you've learned these from back in middle school. So amplitude is also known as the height of the wave. It can be measured up in the middle, like that, or it can be down. Doesn't matter. It is not the total distance, but that distance. The wavelength is crest to crest, trough to trough, or from one point on the wave to the next. So like I could say this part is A, and then the same part is B. That is also wavelength. And by the way, this is called lambda. That's the Greek letter lambda. It kind of looks like an upside down Y. The wavelength is not the sine part of this. It's just the distance from one point to the same point. Okay, so here's our little definitions. These are not terribly hard. You have the crest of the wave, which is the top, the trough, which is the bottom. Now the period is not going to be something you can see on a picture, okay? The period, we're going to use the Greek letter tau, which we used back in centripetal force. The time it takes for a wave to travel, it will be measured in seconds. And then frequency is how many waves pass a point in 1 second. And frequency and period are literally the inverse of each other. And then the last little property, not a little property, it's a big property, jumping in here, is the velocity. Velocity for waves can be found by multiplying the frequency times the wavelength, or the wavelength over time, which is really just distance over time, or if you know the distance in time. But just like any velocity all year, it's meters per second. So let's work through a few examples. All right, first example. The first thing you need to do in a picture like this is know how many waves we're dealing with. So a crest and a trough. So here's a crest, here's a trough. That's one wave. Here's a crest, here's a trough, here's a second wave, and here's a top. So we have 2.5 waves. And I'd have to give you this information. Let's say these take 9 seconds to travel, and that from here to here is 12 meters. All right, so in order to figure out the wavelength, and I'm only putting this here, it's not really an official formula, you take the distance divided by the number of waves. So I'm gonna do a little scratch work over here. So the distance was 12, and the number of waves was 2.5. So let's see what that is. Clear, let's get 12 divided by 2.5, I get 4.8. So each wavelength is 4.8 meters. Okay, the period is the time divided by the waves. So it was 9 seconds divided by 2.5 waves, I get 3.6. All right, frequency is simply 1 over, so this is going to be 1 over 3.6, so I'm just going to go, sorry, I got glare there, just go to the -1 of that. So I'm going to round that to 0.28. The unit for frequency is hertz. That's why it's abbreviated Hz. Now velocity, you can do all of them, and just to show you that it doesn't really matter. Okay, so if I do F lambda, so that's going to be 0.28 times 4.8, or I can do lambda over tau. So lambda was 4.8 over 3.6, or we can do distance over time, and that was 12 over 9. Divided by 9, 1.33. .8 divided by 3.6, 1.33. And 0.28, remember I rounded that, times 4.8, I get 1.34. So it doesn't really matter which one you use. Really doesn't matter because there could be a little bit of rounding. So I'm just going to do 1.33 in wave meters per second. Okay, next one. Let's count the waves. Top and a bottom 1, top and a bottom 2, top and a bottom 3, top and a bottom 4. So I have 4 waves. Adjust that a little bit. All right, so let's do lambda. So lambda is going to be 18 divided by 4. There's 18 meters divided by 4 waves. We're going to get 4.5 meters. Okay, period is the time. So 2.25 divided by 4 waves. Let's round that to 0.56 seconds. And then inverse of that, we can just take it to the -1. Looks like 1.78 hertz. Amplitude, I didn't do amplitude in the other one because we didn't have a scale, but here I have a graph. Even though this is negative, we still see the amplitude is 5 meters. There's no negatives here. And then velocity, you can pick whichever one you want. I'm just going to do F lambda, it's the most common one. So we're going to take 1.78 times 4.5, so 1.78 is 1.5, and we get 8.01. All right, so the last one's going to require some sketching. 3 crests pass a point. So here's a point. So a crest, I just need to get 3 crests. This is not going to be pretty. 2, 3. All right, so there's my waves. This could be the middle. All I care about is from 1, 2, 3 crests. So how many waves is that? Well, there's half of a top, all of a bottom, half of a top. That's 1 wave. Half of a top, all of a bottom, half of a top, 2 waves. Your wave test starts out with this exact type of question where you will have to figure this out. So the number of waves, if I have 3 crests, is 2. Okay? The distance is 20 meters because it says so. And the time, regular time, is 10 seconds. So now it's not terribly different. So lambda is the distance over the wave. So it's going to be 20 over 2 right? 20 meters over 2 waves, it's going to be 10 meters. The period is going to be the time. So it was 10 seconds over 2 waves, so 5 seconds. Frequency is just 1 over the period, so 1 over 5, which I want to put in decimals, 0.2 hertz, it's an equal. And let's use F lambda. Again, frequency is 0.2, lambda was 10, 0.2 times that is going to be 2 meters per second. So that's it. Okay, so you're going to have a bunch of these to practice along with some electromagnetic waves. Remember, when you're doing any formulas with the electromagnetic waves, this will always be the velocity. All right, that's it for now.